Hello students, Gilly here with another video. Here I want to talk about R, specifically optimization of some functions in R. For us, the application here will be maximum likelihood, finding the maximum likelihood estimators. So I hope you'll forgive me, I don't have slides for this. I'll just jump into R straight away and show you a few things. I'm going to assume because this is a third year unit, I'm going to assume you're kind of familiar with R, at least the basic syntax. But if you have any questions, please never hesitate to ask them on the forum. If you're truly lost in R because you've forgotten or maybe you haven't done it before, tell me, okay, and maybe we can find a solution. Last year I was teaching just a little bit of R to first year, so maybe I could even share those videos I made back then. So let me know. Let me know if you have any trouble with R. And as I said before, but let me show you again. In our ed discussion forum, it's quite nice. You can actually run R code directly, right? So if you go to ed, you create a new thread, you want to ask a question, okay, R code something. Maybe you ask it in the right category, R code, and here the point is you can put a code snippet, and this is runnable R code, okay? So R norm of, I'm going to generate 10 random normals. So the point here, you could put your code and run it, point to a mistake or point to something you don't understand or you need help with. Okay, but back to our content. So I'm going to go to R, and here again, I assume you have it on your computers already, or at least you know how to install it. If you have trouble with this, let me know. Okay, so here I have a few lines. I'm going to go over them. Maybe I can share this file later as well. So in fact, here we will have one simple mission. We're going to try to find the maximum likelihood estimators for the gamma distribution. And so we started doing a bit of theoretical work in the slides, but we got stuck because there was an equation we couldn't solve. So maybe I'll make that slightly bigger. I mean, it's already pretty big, but okay, now it's really big, so everyone can see. What do we got here? So I'm going to show you three functions, and hopefully they're all going to work. They're all going to do the same thing. So, but you'll have a few different options. Okay, first things first. Now, for let's say pedagogical value, I'm going to generate data from the computer that's actually distributed like a gamma. Okay, so the gamma will be exactly the right distribution, but this has pedagogical value. Here, kind of arbitrarily, we're going to have a alpha, the shape parameter that's 2, and then a lambda, the rate parameter that's 5. And because the data is kind of truly coming from a gamma, because that's what we're asking the computer, we hope that we're going to get estimates that are going to be close to those values. And if they are, well, we know our procedure has succeeded. Okay, so here, just the syntax is that X will be a collection of points, so a vector. R gamma generates gamma random variables. I want N of them, where N is my sample size. Of course, I could increase this if I wanted to have a bigger sample size. And then here, well, shape is the argument of the function, of the R function, but I feed to this argument my alpha, which is here 2. And rate, again, is the name of the argument of the R function, R gamma, and I feed to it lambda. Okay, this function is very hungry. I feed it my lambda here. Okay, and now, okay, for the now I don't want this. Forget about this. I just want a gamma. Okay, and let's just double check that this works. Okay, if I run this, well, now the objects appear in R, and maybe I can quickly have a plot or a histogram of my data to see what it looks like. Okay, it looks like this. So it's not a symmetrical shape. It's a gamma shape. Now, just quickly, let's find the method of moments estimators. Okay, so those we derive those expression in the lecture slides. Okay, maybe I could quickly go back to the lecture slides just to make sure we agree with those expressions. Here, I just meant for the gamma, we've already done the good work that we found that the method of moments estimator for alpha is this. Okay, the first moment squared divided by blah blah blah, and the lambda is this. Okay, so this is just what I've applied in my R session. Okay, so I find the method of moments estimator here. I just call it AMM for alpha of the method of moments and LMM for alpha of the method of moments. So let's compute them. And let's see, AMM, I get, oh, actually I get very close to the right value. Okay, LMM, okay, I get also very close. Maybe I got slightly lucky. If I did do this again, I'm gonna get a different, sample. If I do this again, I might not get values that are so close. You see here, it's a bit further, but overall, it seems to work decently well because I get, even with the method of moments, I get values that are decently close. Okay, but now that's all good. But to the main topic of finding the maximum likelihood estimators, and as I said, we're going to do this via a few different methods. So the first method is you could say it's like the big guns, the direct maximization, and direct maximization of the log likelihood. And recall the log likelihood has two parameters. So this is a problem where at the same time we maximize the function corresponding to two parameters. And to do this, there's at least two functions in R that can help us. I cannot really tell you if one is better than the other. This is not based on really anything rigorous. In my experience, Optim seems to work a bit better, or at least I get fewer errors usually when I use it. But I cannot say this is like a strong recommendation. So here we're going to try both. Okay, first I define the negative of the log likelihood. Why the negative is because both the functions we're going to use are in fact minimization functions. So they help you to find the minimum of a function, meaning the arguments at which the function is minimal. Now we want the maximum, of course, of the log likelihood. But if we take the negative of the log likelihood, well, minimizing the negative of something is like maximizing the thing itself. Okay, so we create a function which is the negative of the log likelihood. Now this is an expression that would correspond, again, if we go back to the work we've done in the slides. Okay, in the maximum likelihood, it's one of the examples we saw. Find the MLE of the gamma. Now, the log of the likelihood of our data would be this expression. Of course, it's a function of two parameters, alpha and lambda. This is the formula I've implemented in R. Going back to R. Okay, so this would be this long function. Now, the way it works, just careful. Here I'm creating my own function. If you recall, that's the name I give to my function. I assign to it what? Well, a function. Now this function has some arguments, but the way it works, I just need to give it one argument, but this argument is seen as a vector, so it can possibly be multi-value. So here P would be a vector of in two dimensions. So because there's two parameters, okay, meaning P1 is my first parameter, alpha in our case, and P2 would be my my second parameter. Okay, so this equation that now corresponds, careful, to the negative of the expression I had on the slides, the log likelihood. So negative of n times alpha log of lambda. Now minus, again, because it's the minus the log likelihood, minus alpha again minus 1 times the sum. Now here, just careful with the syntax. So because R is a vectorized language, this works, okay, in a compact manner. If I take the sum of the log of x, now x is a vector, log of x is still a vector where the function log is applied element by element. So log is applied to every element of the vector. So now see this log. Let me just show you. If I have any vector, t here, okay, so let's see a vector of just 2, 3, 4, 10, and 200, whatever. That's a vector, okay. T has 5 components here. If I take log of t, it's going to apply log to every element. Okay, so then this is indeed the vector of all the logs. If I take the sum, it's gonna give me the sum. Okay, sum of log of t will give me the sum of all those numbers. Okay, obviously the sum is then no longer a vector; it's a scalar. All right. So now I have a function, and so this function, I define it. Can try that it works in the sense that it's a function. I can pass it a p, but again, remember p is going to be Okay, a vector, if I type 2 and whatever, 2 and 2, 2 and 3, I get something. Okay, the negative log likelihood. I want to minimize this function. Now, those two functions in R, they work well. They have many arguments, but there's only two that are really essential. I need to give some initial values for the search, meaning, okay, where should the function start looking for the values that minimize the function? Here, it's very good. We have already very good guesses because we have the method of moments estimator. So that's a very good first guess. Okay, so for initial values of the search, I'm going to feed to the function the method of moments. Okay, so I'm going to give it a vector. Of course, you know that C creates a vector of the first component being the method of moments estimator of alpha, and the second is the method of moments estimator of lambda. Now here, I'm just finding the MLE, and again, let's try with two different functions. NLM, and by the way, if you recall, if you type the question mark of any function, you're going to get the R documentation about it. Okay, so if you're not satisfied with my explanations and you want to learn more, you can go here and look at all the arguments of the function. But for us here, the first argument is just my function. The second argument is just the initial, your P, the initial parameters for the minimization. And then let's try. Okay, of course, I haven't declared this object, so it doesn't work because I'm a noob. Okay, and then seems to have worked because I don't give an error message. Sometimes you get an error message, but it still worked. It's just going to tell you that there's a warning. This, you need to live with this. It happens quite frequently. But here, it seems that it's good. Okay, we got estimates. They seem to be at least reasonable. It seems to be reasonable answers because we do know that the real parameters are 2 and 5. Okay, very good. Let's try with optim. Like, just note optim as the order of the arguments is reversed. Okay, so yeah, you can learn more about optim if you type this. No, if you type this. Okay, general purpose optimization. Again, if you're in a situation where it fails, usually when it works, you're happy. If it fails, then you go and you check the documentation. You're like, okay, there's many methods implemented there. I don't know them, but maybe one method suits me better, so I can have a look and see if I can play with those parameters and make R bend to your will. But for now, let's try. And then, yes, it works. Okay, I got those. Those are the parameters. Of course, the function returns a bunch of things, but for us, we're happy with the parameters here. Let's see if is it the same. 2.0897. Yes, 2.0897 and 522. Again, 522. Okay, so both give the same thing, or up to a bit of rounding here. So yeah, that's pretty good. Good job. Okay, that seems good. Now, one other method that I think, in this case, I think that the last method we see would be my preferred, because we're gonna take advantage of the extra steps we did with pen and paper. And so just to recall, again, I'm going to go back to the slides. With pen and paper, so what I did now is I maximized this function with respect to two variables at a time. But we have done a bit more work here. Remember, we actually took the derivative of the function with respect to alpha, lambda, and then we got an expression of lambda as function of alpha and the statistics, well, the simple mean. Then we did the same here, and we obtained, so with this bit of extra work, we obtained just one equation of one variable. You see here, because we replaced lambda by what it was here, so we had a different kind of problem where we needed to solve an equation. Okay, so here this is not really a minimization problem; it's just a problem of solving an equation, and we can actually do that in R with the function uniroot that maybe you know already. So uniroot, you feed it a function, and it's going to find the function of, I think it needs to be one variable though. I'm not 100% sure, but I'm pretty sure it needs to be a function of one variable, and it's going to find the roots of the function. But the roots of the function are simply the equations, the solution to the equation function equals 0. Okay, but that's what we have here. Of course, we have a function equals 0. So if we feed to R, the R function uniroot, if we feed it this function, it's going to find the solution to this function equals to 0, which is what we want. So let's do that. Okay, Now, this function is a bit different. It was the derivative of the log likelihood, while here, this actually, it was not really the, oh yeah, it was the derivative of the log likelihood with respect to alpha, and then also with the lambda plugged in. But I think you see what I mean. What I mean by this function, it's the one we had on the slide. Okay, it's n times log of p, blah, blah, blah. Here, p is just a scalar, it's just one value. Okay, it's not the vector. Little p here. So let's try. Now, uniroot, that's what I have here. I put f is the function. So here is just the name of my function. And then it's asking us for an interval in which so the function is defined on some interval. I mean, we give it an interval where it should look for the root. Okay, so we help the function a bit by giving it an interval. Okay, and again, here uniroot, you would find the documentation. Okay, a vector containing the endpoints of the interval to be searched for the root. Okay, exactly. Now here, I don't have very good values to put here, but just because I know that the alpha should be positive, I'm going to put the first bound something close to 0. I don't want to put 0 because putting zeros might cause problem, right? Because there's some logs here, or there's some d gamma. I think d gamma is not defined for 0. D gamma is not defined for 0. Yes. So that's why I'm just putting the value smaller than 0. Slightly bigger than 0. Oh, by the way, d gamma is just a function that's by definition equal to what we had. Okay, the derivative of the gamma function divided by the gamma function itself. Okay. And here the maximum value, I just put it arbitrarily. Okay, 5 times the method of moments estimator. Okay, it should be plenty of room to find the solution. Okay. And let's try. So I mean, if I call this, did I declare this function before? I forgot. If I call this, it's going to give me everything I want. Okay, seems to have worked, no errors. It gives me a root that is, again, that's the value for alpha. Seems very close, 2.0897. Seems very close to what we have had before. Yes. Okay, and then if I declare, if I pass it inside a new variable, I create alpha MLE. So $ root will give me specifically this, which is a solution. Okay, because here you have other arguments. Okay, the value of the function evaluated the solution, you see it's not exactly 0, it's pretty close. This I guess is the number of iterations it took to get the solution. Okay, so let's pass the solution into a new variable called alpha. Let's find lambda, which from our calculations was just alpha divided by m1, by the way, is just the first moment, empirical moment. And I should get the same solution. Okay, 5.22, which is what I got before. So again, I presented 3 methods here. Now, the last one is not really very general because it's really based on the derivation we did. The first one, you're maximizing a function of 2 parameters. You could do that just in general. Obviously, you would have a different expression here for the log likelihood. So I think that's really the core of what I wanted to present. There's a few tutorial problems this week that's going to ask you to apply this, because it's going to be impossible to derive the maximum likelihood estimator by pen and paper. Here, not that it matters that much, but for fun, we could just try. Okay, if we have a wrong guess, I mean, if we're trying to find the parameters that fit the parameters of the gamma, but on a sample size that's normal, I just want to show that it's going to give something relatively reasonable, because if you recall the gamma, if the shape parameter, is it the shape? Yeah, if the shape parameter is quite big, it actually resembles. It actually resembles a normal. Okay, what I mean is histogram of if I generate a gamma of, let's say, size 10,000 with hope I remember that correctly. If the shape is big, let's say 100, and the rate is whatever as before, I think this should resemble a normal. Okay, R gamma generates. Yeah, you see it's pretty symmetrical now. Okay, which means that even if my data is normal, because the gamma is for relatively large values of the shape parameter resembles a normal, I should get some, I can apply the method and probably is going to give me something that's not too bad. Okay, so let's just try. I try again everything with now a sample that's normal. I'm going to declare this again. Okay, I get estimates. Now, those estimates, they're obviously not estimating the values of the normal. They're still trying to fit, it's just that they're trying to fit a gamma to data that's actually normal. But you see, I get the first estimate that's kind of big. Okay, so now, is that really meaningful? I'm not too sure, but let's just try again. Oh, you see, sometimes, okay, well, it gives me the same estimate 23.4. Okay, it still gives me the same thing. It's just that here I did get the warning message. Now, a warning is not the same as error. So a warning, apparently at some steps in the optimization, there were some NAs produced, but I don't think it matters here because we did get the final solution. Okay, and again, we can try same thing here. See if we get the same values again. We should. Okay, 23 and okay, 2.33. Okay, and let's just see what, just for the sake of it, what does it look like if I plot if I generate now a gamma, but with the parameters obtained through the maximum likelihood. Okay, let's see if it looks like let's see if it looks like this, a normal with mean 10 and standard deviation 2. 3.33. Okay, seems not bad. Okay, so a gamma approximation of a normal seems reasonable in this case. Okay, but again, that was not the main point of the video. The main point was to actually find the maximum likelihood estimators. I'll stop here. I know it was a lot of videos this week, but I think it's good to get a lot of stuff out of the way early in the semester to have maybe a slightly more breathable pace a bit later. So yeah, so for your information, if you're thinking it's going a bit fast, I am going a bit faster than last year, but this way I hope that towards the end of the semester we have some time for revision. Okay, so that's some justification for me trying to cover a bit more ground at the beginning. So thanks so much for your following me. Yeah, I'll stop here. I was just verifying that I was sharing the right thing. I would be pissed if I had not been sharing the right thing, but apparently I am. Okay, see you soon.